smaller board, a smaller size K board, in the original size K plus 1. So after you cut into 4 and place a terminal right at the center, so then we have 4 subproblems, each with size K, right? Each with size K. Okay. Then we can form the solution from these 4 subproblems. That means instead of covering the whole board, we cover the ones these 4 subboards are covered. If these 4 subs are covered, very easy, right? We just combine them together without doing anything. So the whole board is covered. So this is what we do. This is what we do for the board problem, for a 2n and 2n board problem. Okay, you see here. So if you can form the solution from the largest size problem from smaller size, then we have to identify this smaller size subproblem. So the way identify for the board case, we divide into 4, and place a terminal on it. So then we also talk about how to form solution from the, in this case we are talking in terms of size K from smaller size. So that can, for the subboard problem, for the board problem, we are talking about forming of size K from size K minus 1. So how to form a solution of size K from a smaller size? For the board case is K minus 1, right? How to form? After we have the solution for size K, nothing need to be done. Just put them together. After the 4 subboard are covered, are fully covered, right? So we just put them together. Nothing need to be done. Nothing need to be done. So, but sometimes we may need to do something depending on the problem. Okay. So this is the second step. This is the first part of the second step. Then the second part of the second step, since we are going to solve the bigger problem from smaller problem, we will go all the way down. So eventually we will reach the smallest problem that can be not be divided anymore, right? So and so for the 2n by 2n board case, the smallest problem is 20 times 20 board. That is for that case is 2 to the power 1 times 2 to the power 1 board. Sorry, 2 to the power 0 times 2 to the power 0 board. Yeah, that is correct. So for the smallest one is 2 to the power 0 times 2 to the power 0 board. That is size K, 0 for the board problem. Yeah. So 2 to the power 0 times 2 to the power 0. So basically only 1 square. So we will talk about the smaller problem, how to solve it directly. Yeah. The smaller problem we have to solve it directly. So for the board housed up covered by terminals, board to be covered by non-overlapping terminals. So the smaller size problem is 2 to the power 0 times 2 to the power 0 board. That is size 0. And for that case, only 1 square, and that is already covered. So we don't need to, because as a problem, it's always a 1 square covered. Yeah. So we don't need to do anything. We don't need to do anything. But sometimes we may have to do something depending on the problem. Okay, then formulate the induction process. Once you do this, once you can do this design, then you can formulate induction process. So under the induction process, we will describe how to solve the smallest problem as a basic step. So the way we solve the smallest problem here, how we solve this one, it will be described by the induction hypothesis here. And how to do it here, sorry. how to do it? How to do this step will be described as basis step. Then how we do under step 2.1 will be described under the inductive step. This is described under inductive step, and this is described under basis step. How to solve the smallest problem already. Okay, so based on 2.2, that is the last one. We describe how to solve the smallest problem as the basis step. So the way to solve the smallest problem we describe as the basis step. And based on 2.1, the first part, we form an induction hypothesis. So in the inductive steps, to state that we can solve those problems with smaller sizes. So for the board case, for the board problem, the second illustrative problem, we will under the induction hypothesis, we will say that we can cover a board of size k. We can cover a board of size k. And how to form solution of one size larger from smaller subproblem, we will describe it under the inductive steps. Okay, so this is according to just on the step I have written down in the previous slide, 2.1, and solve the smaller problem by using the induction hypothesis, because we assume that we can solve the problem of smaller size. So that means we can cover up the board of size k minus 1. And after we put them together, that will be the solution for the whole problem. So this is how we do it in induction step. So how to describe as algorithm? Yeah? So after you form out the induction, after you formulate it as an induction process, the next step is to specify a solution, yeah, using algorithms. So the easier way to specify algorithm to implement a solution from induction is to use recursive structure. Recursion provides an easy and natural structure for translating the induction process into algorithms. So next, we shall elaborate how induction works. Okay, this is the algorithm to specify that in order to find factorial n, okay, we can find it from factorial n minus 1. Okay, the induction process for this one is simple. Okay, now assuming that we don't have a calculator, we want to find factorial n. You know factorial n? N factorial is equal to n times n minus 1 times n minus 2, right? Time until 2 times 1, right? This is n factorial, right? This is n factorial, right? So, if you want to write a program, if you don't have a calculator, how to find factorial n? We can find in this way, right? We can use induction. By using induction, in this case, means that, in this case, we take n as a size. We assume that n is a larger size, right? So we will always form a solution from whether a smaller problem, smaller subproblem. Smaller subproblem can be just one, usually it will be just one size smaller. Okay? So in this case, to find factorial n, we can always find from, if we have the factorial of n minus 1. Because n minus 1 is n minus 1 times n minus 2, etc., right? So if you have n minus 1 factorial, so we can always find n factorial by using n times n minus 1 factorial, right? If we have n minus 1, we can find from a smaller subproblem, n minus 1 factorial. In order for finding factorial n, we can always find from one size smaller, n minus 1 factorial. Once we have this, so we use n times this one, right? So that we will get the solution for n factorial. Okay, so this is an induction idea already. This is an induction idea. So using this induction idea, then if you keep dividing, okay, so just now step 2.2, okay, so by doing this, we will keep reducing the problem to a smaller subproblem, right? So there will be a point that we reach the bottom, right? We reach the bottom, we cannot divide anymore. So in this case, once we did reach 0, we can consider 1 easier. So once we keep go lower down, find subproblem. So 1 is smaller. So 1 we calculate directly. Factorial 1 is 1. We calculate it directly. For factorial 1 we calculate directly. So this is the smallest problem. Okay, and this is how we form the solution of n from solution of n minus 1. Here, this is the way. Yeah. And what are the subproblems in this case? We can form solution for n. This is a subproblem. This is a subproblem. So by following this induction process, then you have the induction hypothesis. Induction hypothesis, you will assume that we can find solution for n minus 1 factorial. Okay, that will be the induction hypothesis. And basis step, what is the basis step? Basis step, we will show how we calculate factorial for 1. 1 factorial is 1. We just take 1. Don't need to multiply anything. And the inductive step, this hypothesis, we can find factorial for n minus 1. Okay? And after that, how to form factorial for n from n minus 1? We just take n. Yeah. We just take n times n minus 1 factorial. That will form. So you can see that the basis step said we can calculate for factorial. In this case, we take 0. Follow here. Factorial 1 is also 0. Also 1. 0 is also 1. So for smaller size, we can take 1 or 0, but since algorithm take 0, we follow here. So factorial 0, the smaller size, okay? So you specify that if n equal to 0, the solution is directly 1. We don't need to go through further calculation. Else, okay? Else, this is the basis step, this is inductive step, okay? Inductive step. Else, how to form solution for factorial n from one size smaller. This is the way. Take n times the solution for n minus 1. Okay? So the whole induction process is very easy to use a recursive algorithm to specify it, as you can see from here. So directly, the recursive algorithm directly corresponds to the induction process. This is the basis step, and this is the inductive step. Form solution for size n from size n minus 1. Okay, so but it does not mean that you cannot use non-recursive algorithm to implement this one. Non-recursive algorithm will not be so direct from the induction process. Yeah, just now the Tower Hanoi example, you will see that. Yeah, the recursive step is very straightforward, but for converting it to the iterative implementation, we introduce some similar to mathematical notation. After that, we work out the formula, right? So we go through quite a number of pages to discuss how to convert recursive to the iterative. But if you implement in recursive, it's very straightforward. Just now, the process, the down if you can write algorithm, yeah, to implement it also. Okay, over here, okay, this is to illustrate to you, since we talk about recursive structure, recursive algorithm, yeah. So how does recursive algorithm work? Yeah? So this is the way the recursive algorithm works. For example, when we use this algorithm to calculate factorial 5, so 5 will be substituted into here. Okay? So initially, then you will check whether 5 equal to 0. 5 is not equal to 0. So you won't return 1. You won't execute this part. You will go to the else. Okay? So the first time you will initiate another execution of this algorithm, right? So if we call factorial 5, you will come here to execute this part. When you execute this statement, you will return 5 times factorial 5 minus 1, right? So that means you will generate a recursive call. That is factorial 5 minus 1. That means factorial 4. So this is the first recursive call. First recursive call. The original call is factorial 5. That generates a recursive call that is factorial 4. And in order to calculate factorial 4, you will use the same algorithm again. We call it recursive because this algorithm call itself, right? Call itself. Factorial 5 is nature. So if an algorithm call itself, that means the algorithm is a recursive algorithm. Okay? So likewise, since it takes 5 times factorial 4, right? So factorial 4, again, we have to execute this algorithm again. Factorial 4, again, is not 0. This part won't be executed. It will execute this part. Return 4 times factorial 4 minus 1, right? So when you want to execute this algorithm for factorial 4, then n will have to be substituted with 4. So when you substitute with 4, you will come here. You will be 4 times factorial again. 4 minus 1, right? So come to factorial 3. That's why. So you call factorial 4, find trigger execution of the same algorithm, but with n substituted with 4. You trigger factorial 4. Then once you call factorial 4, since factorial 4, you will execute the algorithm again, and that activate another call, that's factorial 3. So this is a recursive call, and this is a recursive call. Here, this is a recursive call. This is not a direct call of algorithm. It's activated by factorial 5. So this is a recursive call. This is a recursive call. Factorial 3 will activate factorial 2, and factorial 2 will activate with factorial 1. But all this will be substituted in the algorithm again. Then factorial 1 again will substitute into the algorithm. When factorial 1 come here, it means 1, n will be substituted with 1. Okay. So won't execute this part because 1 is not 0, you will execute 1. That means you will 1, the result will be 1 times factorial 1 minus 1. It means 1 times factorial 0, right? So you will activate factorial 0. This is factorial 0. Again, you will execute the same algorithm by substituting 0 here. Okay? So this 0, so since it's 0, and now equal to 0, so you will execute this part. You won't execute the else. So the if condition is satisfied. So now you return 1. That means factorial 0 does not activate any recursive call. It returns a result directly. 1 with directly. Okay. So then factorial 1 return with factorial 0 return result 1. So once is returned, you return back all the way. Once you have 1, then factorial 1. Okay, so this factorial 1 will be substituted with 1. By substituting for 1 under for the factorial 1 value, you will get factorial 2, go all the way back. So this is how recursive call is activated and executed. Initially, the call is generated from top to bottom. Then the completion is from bottom to top. At the end, everything completed. So in this case, there are how many recursive calls? 1, 2, 3, factorial 4, factorial 3, factorial 2, factorial 1, factorial 0. Altogether 5 recursive calls. When you execute this algorithm with n equal to 5, there are altogether 4 recursive calls. 5 recursive calls, 1, 2, 3, 4, 5. Okay, and this is the way the values are calculated. Here, factorial 0 return, the result is 1. So then once we know factorial 0 is 1, you can calculate factorial 1. Factorial 1 is 1 times factorial 0. That's 1. Then after this, you can calculate the value for factorial 2. That's 2 times factorial 1. So once all these are calculated, you will go back. Then we can calculate the value for factorial 5. So this is how the value are computed. Okay, this is on the recursive call. Okay, next I have written down the algorithm actually for the problem 2. Just now I use it as a reference problem. Okay, so for the board n by n board problem, okay, you can write it as an algorithm using recursive structure. You can see from here. So the name given to this solution is called tau. Tau the board, n, tau the board size n. Let me say 2n by 2n board. You can see from here. So it's all formed by the induction process. If the board is 0, we don't need to do anything. If it's a size 0, we don't need to do anything, right? 2 0 by 2 0 board. That means only one square is fully covered, nothing to be done. So if not, then we divide the original n subboard into n minus 1, 4, divide into 4. N minus 1 subboard, and we put the terminal right in the center, this algorithm. Then after that, we set M1, M2, M3, M4 to be the location of the square that covered by cover. Then we call the same algorithm for 4 subboard. The 4 subproblem solve all the 4 subproblem. Then we don't need to do anything after the 4 subproblem is solved. We don't need anything. That put together is the solution for the whole problem. Okay, so this can be written as an algorithm. The Brown and Hanoi also can be written as algorithm. The 3 steps. If n equal to 0, if there's no this on the tower, we don't need to do anything. Just return the solution. Don't need to do anything. That is a solution. But if it's just remember that if we have n this, if we have k plus 1 this, we always have to move k this in direction not d, right? Then after that, we move the largest this in direction d. Then after that, we move the k this in direction not d again. We always have to do this, right? So this is in fact, this is the description of the step here, the inductive step. Just now for the case of Tau Hanoi, here, over here. Okay, so we describe it as an algorithm move in direction not d. Then here we're talking in terms of k plus 1 from k. It's the same. So in the algorithm we specify n from n minus 1. That's the same. Always lower down to one size smaller. We specify as algorithms. Okay, that's all on the supplementary slide. And now, go back. Okay, there's so much on the induction process. Then, lastly, there are two more algorithms. Two more examples on writing algorithm. These two are simpler than those we discussed. Those algorithms we have already seen. Here talking about in terms of compute the sum of numbers in the array of n numbers. Yeah. So the induction process, how to use induction to compute the sum of numbers in the array of n numbers. Okay? So array we can use n. We can use number of element in the array as size. So first step we need to define size, right? So we use the number of element in the array as a size in this case. And basic step, okay. So n is a size, and so the smaller size. So the basic step we talk about the smaller size, how to compute the sum of an array with the smaller size. Smaller size in this case, we can take the smaller size as empty array, or we can take the smallest size as one element. In this case, we take the smallest array as one element. Okay. So under the basic step, we have to show that we have to show how to compute the sum for the smallest array. Smallest array, there is one element only. So to compute the sum for a number in the array with only one number is very easy, right? Just take the number as a sum, yeah, right? For the smallest array, it's very easy. The sum is just the number. Okay, the smallest array, size 1 in this case, we'll calculate the sum. If it's 4, the sum is 4, only one element, right? So just the number itself will be the sum. Just set the number. So this is how we do. That is how to compute the sum for the smallest array. So that one we have to work out in the basic step. Then after the basic step, we have the inductive step. The inductive step, we look at it for array. Is it possible to compute the sum of array from smaller size? It's very easy, right, to compute the sum of for the number in the array from a smaller size, right? We can compute the sum. If we array have n numbers, n. Okay. We can always compute from array with n minus 1 number, right? If we have the array, let's say this particular array, if we can compute the sum of this n minus 1 number and excluding the first number, with only the first number excluded, if we can compute the sum of n minus 1 number, we just take this sum, right? Just take this sum plus the first number, right? I can do it the other way around also, so I better follow what is written here. Sum of number into it. Okay. In this process, I do it the other way. You guys should follow. So that means if I can compute the sum of this n minus 1 number, excluding the last number, I can always use this sum, assuming this is the sum S method. So for Sn will be Sn minus 1 plus the last number. Last number that is A n minus 1. Got array index from 0 to n minus 1. So I can always compute the sum of the whole array, that is n number, from the sum of first n minus 1 numbers plus the last number. You can always do this. It's very obvious. So this is the inductive process. So for compute the sum, right? N number, first compute the sum of the first n minus 1 number, and we add this number to the last number, okay? Because we have this induction hypothesis, we make use of induction hypothesis. Induction hypothesis, you always assume that we can always we can always solve the problem. In this case, computing the sum from a smaller subproblem. In this case, the smaller subproblem is n, size is n minus 1. It depends on what is needed for you to identify. It can be one size smaller, it can be many size smaller. In this case, it's one size smaller. So we have this. So, and here okay, so this is the process. And after the process, we use an iterative algorithm to implement. We don't use recursive algorithm. You notice in this case, we don't use recursive algorithm. We use iterative algorithms. Okay, so that means we convert this process, this induction process, into iterative implementation. So in this case, it's not difficult to see it. If we just have 3 elements, assuming that we just have 3 elements, 7, 4, 5. Okay, so if you follow the induction step, that means in order to compute the sum of the whole array, S3, I compute it from S2 plus the last number, bracket 2, last number is 2. Okay. Then after that, S2 will be computed as S2 will be computed as S1, right? Lower, smaller, one size smaller, plus A bracket 1, plus then the whole thing again, plus A bracket 2. Then S1 again. Okay, S1 already the smaller, S1 array 1 numbers. Okay. So S1, 1 number only. So I will compute it as what? I'll add the number alone. That is A bracket 0, right? A bracket 0 plus A bracket 1. Okay, so that's why bracket, that means this will be done first. Then after the A, bracket 2. So this is a conversion of the recursive into iterative implementation. You can see that although it's top down, but after you expand it, it's bottom up. A0, in fact, the first element is added to the second element first. The bracket is here. The first element is added to the second element first, then after that, the second element add to then the result we add to the third element. So it is an iterative implementation here. From bottom up implementation. Okay, the other one, again, compute the sum of array n numbers. This is to show you that it can be designed in many ways using induction process. So we compute the sum of number in the array. This induction hypothesis, we know how to. Okay, basic step we always show how to compute the sum. We always show how to solve the problem, solve the smaller size problem. The smaller size problem in this case is with just one number. We just add it to a number, okay, but we form a slightly different inductive step here. So we assume that we know how to compute the sum of number in the array with less than n number. Okay, anything less than n number we know how to compute. So using this hypothesis for computing the sum of number in the array, of n number, first we divide the array into two subarray. Cut it into half. Cut it into two subarray. Then we as close as possible. Next, we compute the sum of the number in both subarray. Compute the sum of this subarray, compute the sum. Because the hypothesis tell us that we can compute the sum of array with less than n number, anything less than n number. Once we cut into two, definitely less than n number. So we can compute the sum of the two subarray. Then after that, we add them up together. Add these two sum together. That we form the sum of the whole array. There's another way. There is another design that we can form from induction process. So follow the induction process. In this case, we use recursive algorithm. So maybe over here, I have to highlight to you that L here is the first index of the array. R here is the last index of the array. First index and the last index of the array. So here, instead of using total number, we have to use index because we always divide due to the reason that we divide the array into half. So we have to count from where to where. So that's why we need the lowest index and highest index to indicate where is your first element and where is your last element in your subarray. Those of you at the back, can you read what I have written on the board? Okay, if this is the array, 8, 9, 3, 7, 4, 5 elements. Okay, 5 elements. Then the whole array, if we want to describe the whole array, then L will be, for the whole array, L will be 0. R will be 4. 0, 1, 2, 3, 4, last index for the whole array. Okay? So now, using this algorithm, that means for finding, so once you call this algorithm sum, then if this is A, then L here, initially L will be 0, R will be 4. Then you check whether I and R equal, L and R. It's not equal, that means it's not the smaller size, it's not just one element. Then we will, since it's not equal, we will execute the else part. Execute else part means return. You add this sum, two sum together, sum IR. For this case, will be A. Okay, L, the first one. So first time you will execute L. So L is this one, 0. You will start from 0 to what? To L minus R minus R. 0 plus 4 divided by 2. Floor, this one represents the floor function. 0 plus 4 divided by 2 is 2. The floor of 2 is still 2. So that means this is sum IR A 0, 2. And the other one, the next one, the next one is sum IR A L plus 0 plus 4 divided by 2. Plus 1. Then is 4. The last one is R. R is 4. So the last part is sum A. This is 2. 2 plus 1, 3. 3, 4. So these two sum will be added up together. That means the first one you will calculate the sum from 0